welcome to the first lesson for Year 10 Specialist Mathematics. Generally, with Specialist Mathematics, we start with an introduction to set notation because it becomes a very big part of the way that we structure questions and the way that we communicate mathematics. So basically, the idea here is that this is a basis of the language of mathematics that we're going to apply throughout the course over the next couple of years. The intent is not to be fully fluent with this at the end of the lesson, but to set a foundation so that as we continue forwards, you've got a good understanding or a decent understanding that you can build on of the language that we're going to utilize. And you'll be able to read mathematical statements using set notation and be able to decipher what the question is asking. Okay, so basically this lesson is an introduction to set terminology and language. We'll use a little bit of set notation, and then we'll try to apply it into some finite sets. So I've got a bit of a structure that's set out. I'm going to build on it. We'll use some of the notation as we're going through. So you can see here that I've got a list of different things I'm going to talk about. That's mostly so I don't forget specific things. Now, obviously, the first thing is we need to know what a set is. And a set here is a collection of numbers or values or items, basically. So a simple set that I could define is that A is equal to. Now, these are our set brackets. These curly brackets allow us to define a set. And within that set, I can either define a finite or an infinite amount of values. So let's say we look at 1, 2, 3, 4, and I close off my set. That's a finite amount of values. There's 4 values in there, and there can't be any more. So my set A is finite. So here is an example of a finite set. It includes the values 1, 2, 3, 4. The values within we usually refer to as elements. So A is a set with elements 1, 2, 3, and 4. Now for an infinite set, the idea is that there's infinite values that exist within it. So one way to do that would be that we have a set 0, 1, 2, 3, ... So that ... means that that's going to continue indefinitely. So approaching positive infinity, going up in integers, so we can see that we're counting from 0 onwards. There are a number of infinite sets that we refer to. So instead of having to state these most of the time, we'll refer to these infinite sets below. So we can see here, infinite sets, and we've got R. Now that is real numbers. And real numbers basically encapsulates any real number you can think of. So it includes decimals, which are reoccurring, terminating, and so on, all fractions, surds. So remember that surds are things like square root of 3, transcendental numbers like pi, Euler's number, and so on. So any number that's a real number can exist in this set of real numbers. Now, it's contained between negative infinity up to positive infinity. So pretty much any number you can think of exists in that set real numbers. Natural numbers are a set of counting numbers. So natural numbers starts at 1. So we've got a set that starts at 1 and then increases in whole numbers up to positive infinity. So a set of natural numbers could be written just as that, starting at 1. Now, if I want to include 0, it is whole numbers. So whole numbers starts at 0, and then we count to infinity. Z or J is integers, and integers are starting at negative infinity, so ... -2, -1, 0, 1, 2, and so on. So integers include negative numbers. I should be writing what these are. So this is natural numbers, whole numbers, and integers. And the last one I'll state is Q, which is really hard to draw. And these are rational numbers. And rational numbers are anything that can be shown in the form A on B. So any fraction or any decimal that can be converted to a fraction. We have other things like irrational numbers, complex numbers, and so on that we'll deal with later on when we're looking at other units. Okay, so those infinite sets become really useful because they allow us to define which numbers are involved in a question before we start. So these infinite sets will be something we come back to all the time. Okay, so the next thing is an element, and we said that an element is just a value within a set. The symbol we use for element is this one. So it looks like a bit of a capital E. We might say something like 2 is an element of a set of integers, and there's a truthful statement. Or we might say simply that 3 is an element of that set A that we defined earlier. Now, if we had to say not an element, so it's very similar. So if we can write our element sign, so we write our element sign and we put a cross through it. If I wanted to say that -2 is not an element of the set A, then I could say that. So just a mathematical statement language here, -2 is not an element of A. The next term is a subset. Now, a subset is a useful term. If we say something is a subset of something else, and that means every element within a set is an element of a second set. So let's say that set A is 1 and 2, and set B is 1, 2, 3, and 4, and set C is 0, 1, 2. Then we can start making statements here. So we could say, we probably need to define the symbol for subset. So subset can be that, so it's like a C, or it can be the same symbol with a line underneath. So those two symbols are the ones that we use for subset. Now I can make some statements here. I can say A is a subset of B because every element within A exists in B. I can also say that A is a subset of C. So that's because all the elements in A exist in C. Now, if a set is not a subset of the other, then we can do a very similar thing that we did with the element. We can write our symbol, and we can put a cross through it, or the preferred symbol with a line underneath, cross. Let's see, well, we know that C is not a subset of B because it has that 0 in it. All the elements in C do not exist in B. And we can also say that C is not a subset of A, and so on. Now, just for your knowledge, I don't think you'll have to use this too often, but if I have set A, then if I wanted to look at all the subsets of A, then the first one that we have to consider is a null set. So if we have no values, that's a subset of A. That's something that is possible by selecting values from A or not select. So the next one would be that it could be 1, it could also be 2, or we could select both of them, 1 and 2. Now the order doesn't matter, so stating a set with 2, 1 rather than 1, 2 is unnecessary. Okay, so there are our subsets of A. Now a universal set, and usually we use omega for this, or we use a xi. It's one that I can't really draw, so I can't help you with that symbol. But those two symbols are what defines a universal set, and a universal set is a set for a given question such that all other sets are a subset. So it's basically all the elements considered in a situation. All right, we use these for Venn diagrams a lot. We go, well, there's 20 kids in a class, so the universal set includes the 20 kids. All right, some other common symbols, intersection, and so that's a combination of two sets. So we're looking at a crossover, or which elements exist in both sets. A union is, again, it's another combination of two sets. In this case, it's all values combined. So it's the values that exist in one or both. Now, these symbols should be familiar from Year 9 mathematics. For all, this symbol allows you to apply some operation or process to the variables you're using within a set. So we might say something like a plus b for all values a and b, which are elements of a set of real numbers. So that's saying that we'll consider the sum of all values a and b, where a and b just have to be a real number, such that it sets a condition to some elements, or it sets a condition to define a set. We might say something like x such that 2x plus 3 is equal to 5. Now from that, we might define a set, so we can say that this set is equal to a. Now when we go and solve this 2x plus 3 is equal to 5, we end up with x is equal to 1. So that means that set A is 1. So we can see here that that's such that allows us to determine that condition for the set to be considered. A null set is just an empty set, and that is a symbol we use. A complement is the alternate set. So let's say if we look at a universal set that is 1, 2, 3, 4. So remember that universal set is the conditions for our scenario. So these are all the possible values. If we say that set A is equal to 1 and 2, then not A will be equal to the remaining, so 3 and 4. This not A is the complement. So A and not A together represent the whole universal set. The complement is the other values. So it's easy to think of it as not whatever that set is. So we should know that the combination of A and not A will give us that whole universal set. So a disjoint set, which we don't use very often, is disjoint sets are sets where there is no common elements. So that is, if we have set A, which is 1, 2, and 3, and set B, which is 4, 5, 6, then these are disjoint sets because there's no common. So we can say that the intersection between A and B is a null set. There's no common elements. This is something we'll use a lot over the next couple of terms, cardinality. Cardinality is basically the number of items within a set. So sometimes it's easier to talk about how many values are within a set rather than talking about the value specifically in the set. So if set A is 1, 2, 3, then the cardinality of A, so we can see it's represented with A and the two lines, so it looks like a modulus or an absolute value. The cardinality of A is 3, or there's 3 values within A. We can also write that as n bracket A, so the number of items within A is equal to 3. Now the final statement is not including. So if we're not going to include a value within a set, or we want to remove a value within a set, we're just using a backslash, and the values within the set will be removed. So if we wanted to, say, look at every value except for 0, so every value except for 0, and I'll just scroll up a little bit, we could say that we could say a set of real numbers leaving out 0. Okay, so here's a couple of statements we want to try and understand. Here we've got n, and we've got that symbol for all, and then n element of integers, but we've got a plus there, which means positive integers. So this is saying some value n for all values n of n, which are elements of a set of positive integers. So basically, we're saying that this gives us a set including all positive integers. So 0 isn't a positive integer. The first one is 1 up to positive infinity. So all these values can be n. Now, if we wanted to add that n in there, we could say that our set is n such that, 1, 2, 3, 4, up to positive infinity. Okay, so our second one here is that set A is a set with a, or little a, such that 2a is plus 1 is greater than 5. If we can solve this inequality, then that gives us all the values that a can be. So we've got 2a plus 1 is greater than 5. Subtract 1, we've got 2a is greater than 4, divide by 2, and a is greater than 2. So that means the first value that a would be 3 and 4, and that will go through to positive infinity. Now, that is a little bit open to interpretation. Possibly, if we're talking about real numbers, then it can just be any real number that's greater than 3. We'll take it as if it was meant to be integers. Now, last one here, we've got a such that a is greater than negative 2. So we're looking at negative 1 and 0 and so on. And we've got b such that b, so this sign here, the intersection, means that both must be true. So we're looking for the crossover of both. So which elements are true for each? So b less than or equal to 7. So 7 is the biggest number, 6, 5, and so on. Now we're excluding 0. So now we should be able to look at a set here. Okay, so a set includes negative 1, obviously. No 0, but it does include 1, 2, 3, 4, 5, 6, and 7. It's less than or equal to 7, so 7 is included. And that's all our values within this finite set that's been determined. So again, I'm going to assume that we're considering integers only. All right, so that's a whole lot of language, and it will take you time to get used to it. And you want to flick back to this and try to decipher as much as you can. That will take time. So the goal is not today being experts, but in the long run being able to read and interpret using set notation. All right, so the rest of this is just going through a bunch of examples. Hopefully we'll be able to interpret and solve these without too many issues. So the first one, we've got a set C. And C exists such that 5x is equal to 20. So let's first solve this 5x is equal to 20. We know that means that x is equal to 4. Now what that means is that set C includes the element 4. So if we look at this statement, C is equal to 4, I'm hoping that we can see the difference between these. This one here is not true, because C is a set, and a set contains element. C is not the number 4, but it's a set that includes the element 4. So these two things are distinctly different. C is a set, C is not an individual element. All right, second question. Which of these sets are equal? So we've got the set ABC, CBA, BAC, CAB. Now I'm hoping that everybody remembers from earlier that the order of sets is not important. So in this case, that means that all sets are the same. So as long as we keep that in mind, the order of sets is not important. So these sets, ABC, CBA, are the same because they include the same elements. All right. So we've got set K in the next example. So it's asking us to show that set K, which is the integers 1 to 9 inclusive, is not a subset of P is equal to X such that X is less than 9. So this is where we have to be really careful. We're saying that X such that X is less than 9. If we take this as integer a whole number of values, 9 is the biggest, or 9 is not the biggest value. 8 is, because it's less than 9, and 7, 6, and we're going to keep on going down to negative infinity. So this includes negative. Now the big thing is that we're just trying to look at K as a subset of P. So we know now the values in P. The difference is that P does not include 9. So K cannot be a subset of P because P doesn't include 9. So not a subset. So keep on moving forward. Example 4. So first of all, we're looking at the set C, which is equal to Y, such that Y is not equal to Y. Now, how many numbers do we know that are not equal to themselves? And I can't think of any that exist. So C will be a null set because there's no numbers Y that aren't equal to themselves. All right, so first one is a null set. C is a null set. When we look at M, we've got P plus 5 is equal to 5. We can solve this equation and we end up with P is equal to 0. Now, 0 is an element, and therefore M cannot be null. So M is equal to a set that includes an element which is 0, not a null set. When we look at the third one, we've got M such that M squared is equal to 16. And this end here is really important, so both have to be considered. And 4M is equal to 12. So if we solve each of these, we can say that M is equal to plus or minus the square root of 16. So M is equal to plus or minus 4. Remember, when we undo an even power, when we do the inverse operation, we always have to consider both positive and negative. So M could be positive 4 or negative 4. And over here we get M is equal to 3. So we've got two outcomes there. We're looking at end. So we're looking for the elements that are true for both of those equations. And the answer is there is none. So therefore, T is also a null set. None of those answers correspond and are both true. All right, if we move forwards, we're looking at example 5. Now this should be nice and easy. This is just writing in set notation. So we just have to know our terminology, and then we can write out M is a subset of Q, so M is a subset of Q. Nice and easy. B, 12 is an element of Y. So 12 is an element of Y. K is a set with no elements, so we've got K is null set. F is not a subset of Q, so F not a subset, so subset with cross through of set Q. 21 is not an element of P, so 21 is not an element of the cross of P. 3 is contained in D, so that means that 3 is an element in set D, so 3 is an element of set D. U does not belong to H, so U is not an element of H, and U and V have exactly the same elements, so U is equal to set V. Okay, so nice and easy. You'll get better at this as you go along as well. The last example is we're going to just rewrite the following, explicitly listing the elements rather than the statements within. So let's start with A. We got P is equal to. Now G is a letter in the word establishment. So basically, we're just taking all the individual letters in establishment. So we've got A, E, S, T, B, L, I, H, M. Now we don't put E again. Remember, we don't repeat elements. So E's already there. We don't have N, and T's already there. So there's our elements of the set P. We look at B, we've got an equation, so X such that 5X plus 12 is equal to 2. If we can solve this and get the values for X, then we can determine the elements within set F. So 5X is negative 10. X is equal to negative 2, and that leads us to F is a set with the element negative 2. Look at C, we've got set L, M such that M is a digit in the number 27872. So we're just looking at digits here. So L includes the elements. We've got a 2, we have a 7, we have an 8, and then we've got 7, 2. Again, we don't repeat those elements again, so L is simply 278. When we look at D, we've got set M and we've got y such that y squared takes 6y plus 9 is equal to 0. Now, we know that that's quadratic, and possibly some of you can see that that's a perfect square. If not, I'll take the A, C, and B decomposition approach. AC is 9, B is negative 6, we're using negative 3 by negative 3, and negative 3 plus negative 3. We can see this is a monic quadratic, so it just factorizes to x take 3, x take 3, or x take 3 squared. And using null factor theorem, we end up with x is equal to 3. Now, I don't know why I did it. It's just habit. All those x's should have been y's, and I should be saying that y is equal to 3 and not x. So that leads us to our set M, only including the value 3. Now, our last one is we've got another one of those and symbols. So we've got z such that z squared is equal to 16, and we've got 3z plus 18 is equal to 6. So if we solve both of these, first of all, z is equal to plus or minus square root of 16, which is plus or minus 4. And if we solve the other side, we've got 3z is equal to negative 12. When we divide by 3, we have z is equal to negative 4. So at negative 4, over here we've got z is equal to 4 or negative 4. So the intersection here, the element that exists in both sides is negative 4. And that gives us our final answer that set U is a set with an element negative 4. Okay, so I know there's lots in there. There's heaps of examples. What you'll do now is you'll go and practice questions that are similar, build up some of your skills, and hopefully get to a point where you can read and interpret at a relatively good level. Okay, thank you.